Hello, Dr. Ryu and everyone. My name is Phương Trân, and today I'm presenting how nuclear magnetic resonance based metabolomic helps to identify ischemic stroke. As we know, ischemic stroke is one of the serious public health globally, so finding the biomarkers for ischemic stroke is very crucial and important. There are different types of metabolomic method, but the reference type is nuclear magnetic resonance. So today we will look at how the NMR can be used to identify the biomarkers of ischemic stroke. And these are the steps to identify the biomarkers. First one is sample generation, sample preparation, data acquisition, data analysis, and biological interpretation. Moving on to the principle, NMR is a very high throughput analysis. It's based on the magnetic spin properties of atomic nuclear, and the most widely used atomic nuclear is hydrogen because it has the most natural abundance. The theory behind the NMR comes from the spin of nucleus, and it generates a magnetic field. So as we can see here, without the magnetic field applied, the nuclear spins are random directions, but when there's a magnetic field present, the nuclei align themselves either with or against the field of external magnet. So if the external magnetic field is applied, the energy transfer is produced between the ground state and excited state. So when the spin returns to ground state, the absorbed radio frequency energy is emitted at the same frequency level. And this emitted radio frequency signal can give the NMR spectrum of the concerned nucleus. Now, there are advantages and disadvantages of this method. For the advantages, NMR is very straightforward operation. It has short analysis time and inexpensive. And for disadvantage, NMR can produce overlapping peak phenomenon. Sample generations. So they used 60 male rats, and then the rats were randomly divided into two groups, which is sham group and MCAO groups. Sham group is surgical procedure without surgical incision, and MCAO groups usually based on the reperfusion time. CSF sample collection. So the rats were anesthetized with 10% of chlorohydrate, and then the sample was drawn into the syringe by simple aspiration. It usually yields 100 to 120 milliliter of CSF per rat, and then the sample was centrifuged at 4 degrees Celsius for 10 minutes and stored at negative 80 degrees for sample preparation. After being allowed to defrost at room temperature, 100 micro CSF plus 10 microliter of TSP in heavy water and 500 milliliter of heavy water were mixed and centrifuged for 10 minutes. And then after that, 550 microliter solution were pipetted into a 5 milliliter of NMR tube for analysis. For the data acquisition and statistical analysis, So the sample was loaded and dissolved in a solvent, and then it placed in a magnetic field where the tubes will spin, and then a radio frequency generator then irradiates the sample with short pulse of radiation, and it causing the resonance. And then when the nuclear falls back to um, their lower energy state, the detector measure the energy release, and the spectrum is recorded. So here is the spectrum and how it looks like. And after that they apply a partial least squares discriminant analysis, or PLSDA. This will allow discrimination between metabolites and identify the metabolites. So the Y acid is the intensity, and the X acid is for magnetic field strength, and the circle usually present all the metabolic pathways potentially involving a class separation, and increase color tone towards red. As we can see here, there are some reds right here. It indicate the pathway of higher impact. After the metabolites were identified by the PLSDA loading plot, the NMR t-tests were applied to evaluate the responses of these specific metabolites beside the shame and MCAO groups. In addition, the data were expressed as the mean plus minus standard deviation and the p-values. If it's smaller than 0.05, then it indicates the statistically significant. Metabolites changing between shame and MCAO groups. So here are the most distinctive metabolic changes in MCAO groups as a result. As we can see, most of them are increased. Most of the metabolites are increased, but some of them are decreased, which is the glucose, glycine, L-serine, myo-inositol, and citric acid. And they all reveal the pathophysiological process of ischemic stroke. So we can see here, as I just told you earlier, most of them are increased, and you can see here glucose decrease, glycine also decrease, as well as serine, myo-inositol, and citric acid. And here are the table of NMR t-test. So yeah, as we can see here, the D represent for the clinically significant, which is smaller than P smaller than 0.05. So these are the significant metabolites that help to identify the biomarker, which are creatinine, glucose, inositol, ketone bodies, and these two they are not shown in the data, which is glutamate and GABA, but they are very important. Um, for the glutamate, it usually increase in CSF at 6 hours after reperfusion. It then decreased to normal at 24 hours after reperfusion. And then the GABA, it increased offers at 12 hours after reperfusion, but usually later than the glutamate peak time. And so on the table that we just saw earlier, there are 27 metabolites that were changed significantly, and potential biomarkers are acetic acid, 3-hydroxyvaleric acid, 3-hydroxybutyric acid, choline, L-alanine, creatine, glycine, pyruvic acid, glycerol, glutamic acid, D-fructose, lactic acid, and acetone. NMR method helps us to understand the biochemical metabolite changes in CSF of ischemic stroke and reperfusion rats in early stage, and metabolics may have the potential to become a clinically helpful diagnostic tool for ischemic brain injury in the future. Alright, that's it for my presentation. Thank you.